Hello students, welcome back to the session, that is the second session of accelerators. So in this session we will be learning about what do you mean by linear accelerators. We have seen two different types of accelerators. One is cyclic accelerator and the linear accelerator. So what is the basic need of accelerator means we have understood that in order to study the properties of the nucleus we have to induce the nuclear reactions, so we need a projectile. So that is, we have to increase the energy of the charged particles like alpha particle, proton, beta particle to high energies. So in order to do this we need accelerators, that is the device which is used to increase the energy of the charged particles is what we called as an accelerators. So depending upon the path that is being followed by the charged particles in the accelerators, we will divide the accelerators into basically two types. One is the cyclic accelerator and the second one is the linear accelerator. So in case of cyclic accelerator, for example, for cyclic accelerator was cyclotron. So we had seen that the path of the charged particle, that is positive ion, was in the circular path, right? So here we are studying about linear accelerator, that is the path of the charged particles will be a straight line in case of linear accelerator. So linear accelerator can be defined as a device which accelerates the charged particle. So linear accelerator is a device which is used to accelerate the charged particles or ions along a straight line. So this type of accelerator is what we call it as linear accelerator. So here we have the electric field, okay, in order to accelerate the that is a charged particle by applying an oscillating electric field. So in the linear accelerator we are using the electric field, that is oscillating electric field, to accelerate the charged particles. So the shape of the accelerator will mainly depend upon, that is the shape of the linear accelerator will depend upon the particle that is being used to acceleration. That is, if you are using electron, the design of the linear accelerator will be one type, and if you are using proton, the design will be different. Okay, so therefore depending upon the type of the charged particle, so the design of the linear accelerator will also change. So in this diagram what we are seeing here, it is what we called as a drift tube accelerator. So this device what you are seeing in the diagram is known as drift tube accelerator. So what is the principle of this? So now let us study what is the principle. Next we shall go for the construction. So once again we have to recall, that is the wave nature of material particles. So we all know that whenever any charged particle is in motion, it will be, that is any material particle in motion, then it will be definitely associated with the wave nature. So what is the principle of this drift tube accelerator is that whenever any charged particle or ions, basically they are material particles like electron, proton, ions, they are material particles, right? So when these charged particles or ions, if they are passing through the accelerator and if they are accelerated, and if the frequency of the applied electric field, okay, so I said that is will be applying the oscillating electric field. So if the frequency of this oscillating electric field, if it is equal to the frequency of the motion of the particles, then in the linear accelerator all the, that is charged particles will get accelerated if the electromagnetic wave, that is nothing but the wave nature associated with the material particle, that is its phase velocity is equal to the velocity of the charged particle, then definitely the charged particles will get accelerated. Now let us see once again the principle. So we all know that whenever any charged particle is in motion, it will be associated with the wave. That is, any material particle in motion will be associated with the wave nature. So if the frequency of the applied electric field or oscillating electric field, if it is equal or if it is in resonance, that is if any two frequencies are equal, then we say the condition for resonance. So if the frequency of the oscillating electric field and the wave motion of the particles, if they are equal, then there is the electromagnetic waves whose phase velocity, if it is equal to the velocity of the charged particle that is being getting accelerated, if these two are getting equal, then the charged particle will definitely get accelerated to a very high velocity. Okay. So now let us look into the construction part, that is the construction of the drift tube accelerator. So in this diagram we can see that there is the drift tube accelerator consists of a coaxially placed hollow metal cylinders. So these metal cylinders or hollow metal cylinders are what we call it as an electrodes, or they are also called as the drift tubes. Okay, so we can see that the drift tubes length, that is the successive tubes, are having increasing length. So if you compare the length of this tube and this tube, okay, let us take it as this as tube number 1 and this as tube number 2, we can see that the length is increasing, right? So the length of this is less than the length of this, and similarly the length of the second electrode or the second tube will be less than the third one. So therefore it will be having linearly, that is successively coming tubes will be having increasing length. Okay, and they are placed such that the axis or they are coaxially placed, that is the axis will pass through the same point. Okay, so the alternating cylinders are connected together. That means, so if this is the first cylinder, second, third, fourth, fifth, sixth and so on. Okay, so this odd number cylinders are connected to one end of the oscillating electric field source, and the even number that is second, fourth and sixth. Okay, so these tubes will be connected to the other end of this oscillating, there is a oscillating electric field source. So what is the intention in the connecting, that is the first electrode or the first tube, second tube, first tube, third tube and fifth tube to the one end of the oscillator, and second tube, fourth tube and sixth tube, that is the even numbered tubes to the other end of the oscillator, is that, see, whenever any there is the oscillator which is connected, okay, to these tubes. So if if these, so in one or in the first half of the cycle that is generated by this that is oscillator, if the tube 1 and 3 are positive, second and fourth will be negative. That is, if the first tube and the third tube is under positive potential, then definitely second and the fourth the tubes or the electrodes will be under negative potential. So this is in the first half. So in the second half, what happens? Since it was positive in the first half of the cycle, that is the AC cycle, the field will be reversed. That is, the first tube will be negative now, second tube will be positive, third tube will be negative, and this will be positive, and so on. Okay, so look into this diagram once again. Here we have the first tube, second tube, third tube, fourth tube, fifth tube, sixth tube and so on. Okay, so here what we are doing is, so we are adjusting the frequency of this radio frequency oscillator such that if during the first half of the cycle of this oscillator, if the first tube is positive, third tube will be positive and fifth tube will be positive. That is, all the odd tubes will be under positive potential and all the even numbered tubes will be under negative potential. That is, second tube, fourth tube and sixth tube will be under negative potential. Now, during the second half of the cycle, so the first tube will be under negative potential now, second tube will be under positive potential. That is, the potentials of even and odd number of tubes have been interchanged. So this is the construction of the linear, that is a drift tube accelerator or the linear accelerator. So now where are the charged particles are getting accelerated? So the ions or the particles, okay, are getting accelerated in the gap between the two successive electrodes or the tubes. Okay, so we can see a small gap here between these two, and here also we have a small gap. So the charged particles will get accelerated in the gap between these successive electrodes. Okay, now the ions, okay, will travel with a constant velocity inside the tube. Okay, remember students, the charged particles are accelerated in the gap between the tubes or the electrodes. Okay, so these tubes can also be called as the electrodes. So here the charged particles are getting accelerated. So I'll show you how. And inside the tubes or inside the electrodes, they move with a constant velocity. Okay, so this is how it works. Okay, now during working of this linear accelerator, we will explain how the charged particles are getting accelerated in the gap between the tubes. Now let us see how does this linear accelerator or drift tube accelerator works. See, for any accelerator, we need a source of charged particles. So we have considered some source of charged particles such that this source will produce positive ions. So these ions, that is the positive ions which are produced from the source, are entering into the axis of the accelerator through an aperture or a small hole, that is what we call it as an A. In this diagram you can see that we have a small gap between this source and this aperture. Aperture is a small opening, here you can see. So these source, that is the charged particles which are produced by this source, are entering this accelerator around or along this aperture A. Okay, suppose this charged particle, that is the positive ions, leaves the aperture A. Okay, and during the half of the cycle of this oscillator, so the charged particle is accelerated. So that is, this tube 1 or electrode E1 will be under negative potential with respect to A. Okay, so during positive cycle, during the construction, we have studied that during positive cycle or during first half of the cycle, an odd number tubes will be under negative potential and these will be under positive potential, and during the next cycle the thing will get reversed, that is odd number tube will get a positive potential and even number tubes will get the negative potential. Okay, so we have studied that. So now during the first half of the cycle of the oscillator, E1, that is electrode E1 or the tube E1, will be under negative potential with respect to this aperture A. So what happens, the gap between this aperture A and the tube 1, okay, so we have a certain gap here. So in this gap, the charged particles get accelerated. Why? Because they are getting accelerated or they are getting attracted towards this electrode E1. So as usually what happens, they get accelerated because of the electric field that we have applied. Now when the tube, that is a drift tube 1 is negative with respect to A. So if E is the charge of the positive ion, or let us consider the proton. Okay, so if you are not considering E, you can consider Q in general, no problem. Okay, there is no restriction that we should take only E. You can also take it as Q. Okay, so but here I have considered the proton, okay, so as a source of positive charge. So I am going to take the charge of proton as E. Okay, so if E is the charge of the charged particle, that is the positive charge, and m is its mass, and v is the potential difference applied. Okay, so then from the law of conservation of energy, we can show that there is a half m v1 square, that is nothing but the kinetic energy of the charged particle, is equal to v into E, where v into E is nothing but the potential energy. We all know about this. So if I calculate the velocity, I can write it as 2 into v into E divided by m, or v1 is equal to square root of 2 into v into E divided by m. So this is the velocity of the charged particle on reaching the drift tube. Okay, so that is which is having a length of certain length L1, let us consider. Okay, so this is the velocity. Now the length of the tube 1, okay, so here we have the length of the tube 1, first tube, is so adjusted such that as the positive ion or the positive charge comes out of it, that is when it comes out from the first tube, the tube has, that is the second tube will have a that is it will be under positive potential initially. Now due to the adjustment in the frequency of the oscillator, now the second tube will become negative. Initially So it was adjusted such that this was under negative potential with respect to the aperture A. Now the frequency of and the length of the first tube is so adjusted such that by the time the charged particle comes in the gap between the first tube and the second tube, this second tube potential will get interchanged from positive to negative. Why? Because here you are using this positive source. Okay, there is a positive protons, positively charged protons. So as soon as this proton comes out from the first tube, the second tube must be so adjusted, that is the frequency of the oscillator is so adjusted such that the tube E2 must be under negative potential with respect to E1. Okay, so the frequency will be adjusted in such a manner. Now the positive again is, that is the positive charge is again accelerated between the space of the tube 1 and tube 2. Now here in the second tube, if I consider there is half m v2 square, where v2 is the velocity of the charged particle in the second tube, such that the potential will be equal to twice the initial potential. Okay, so this is a condition. Okay, such that the frequency of the oscillator and the motion of this charged particle inside the tube. So if these two frequencies are adjusted such that, so the kinetic energy must be equal to the applied potential. So this is a condition for resonance. Let us consider. So half mv2 square is equal to 2 into v into e. Or if you solve this, we'll get v2 is equal to, or v2 square is equal to 2 into v into e divided by m. So if you take the square root on to the right hand side, it will be square root of 2 into square root of 2 into v into e divided by m. If you look at this equation, here we have square root of 2 into v into e divided by m. Here also we have square root of 2 into v into e divided by m. So therefore I can write v2 is equal to square root of 2 into v1. So the velocity of the ion in the second tube must be equal to square root of 2 times the velocity in the first tube. Okay, so this is the second equation that we have got. See, from this we can say that is the length of the second tube must be equal to square root 2 times the length of the first tube. Okay, so if L1 is the length of the first tube and L2 is the length of the second tube and L3 is the length of the third tube, then the ratio of the lengths of the first two, second and the third tubes can be written as in the form 1 is to root 2 is to root 3. Okay, and remember that students, since the accelerator is having a varying length, okay, that is each tube is having are having increasing length. So as soon as the polarity of this tubes changes, okay, so the charged particle should arrive in the gap between the two ions, gap between the two tubes. So therefore the time taken by the charged particles to travel this length, that is the increasing length, must be equal, such that as it comes in between the gaps of the tubes, successive tubes, the polarity is being changing continuously. Initially here it was it was under negative potential with respect to aperture. As soon as it came out of this first tube, the potential of the second tube became negative and this became positive. Similarly, when this charged particle comes out of the second tube, the potential of this third tube must be negative and this must be positive, such that it can accelerate towards the E3, that is the third tube. So similarly here we can see that the length of the third tube is square root of 3 times than the first one. So therefore the time taken by the charged particle to travel this length must be equal to the time taken by the charged particle to travel this length. So if at all this time, that is the time taken by the charged particle in all the tubes, if it is same, then only the frequency of this charged particle and the frequency of this oscillator will get synchronized, such that as soon as it comes out of the tube, it gets accelerated, or the potential of this tubes goes on changing. Okay, so that must be remembered. Now if there are n number of gaps that is been encountered by the charged particle when it travels in the accelerator, and Vn is the final velocity. Okay, so then we can write the velocity of the charged particle as soon as it emerges out from the nth tube will be equal to square root of n times the velocity of the charged particle in the first tube. So since the ions are traveling with gradually increasing velocities through the successive tubes, it is necessary for the length of the tubes to maintain a resonance condition. So now the time taken by the positively charged particle to traverse or to travel through this drift tube at any stage, okay, that must be equal to the half the time period of the oscillator. So remember that half the time period of the oscillator. If this time is equal to the length travelled by the charged particle in the successive tubes, then only the condition for the resonance can be achieved. So therefore, the time taken to traverse by the charged particle at any stage, okay, must be equal to half the time period of the oscillator. Okay. Now we have taken, that is Vn is the velocity of the ion, and the time taken by the charged particle to travel the nth cylinder is as Ln. Okay, that is Ln is the length of the nth cylinder. Then the time taken to travel this length with the velocity Vn must be equal to half the time period of the oscillator. Okay. Now, so this can be obtained as, that is the length of this tube can be obtained as Vn divided by 2 into nu. Okay, so here see, here we have T by 2. Okay, so this is written as 1 divided by 2 as it is. So into nu. Okay, so nu is the frequency which is inversely proportional to the time period. So it is 1 by nu. Time period is written as 1 by nu into this velocity Vn. Got it? Okay. Sorry, strike out this Vn because we are talking about only T by 2. So it is 1 divided by 2 into nu. Okay. Now here we have, there is Ln by Vn on the left hand side. So this must be equal to 1 divided by 2 into nu. Okay. So the previous equation we have Ln by Vn is equal to 1 divided by 2 into nu. So we can write Ln is equal to Vn divided by 2 into nu. So which can be written as 1 divided by 2 into nu. So Vn, we have the equation as 2 into n into E into, this is capital V potential, divided by m. Okay. So and here we can see that the final energy of the charged particle which is coming out of the accelerator will mainly depend on the number of gaps and energy that is being maintained or energy that is being gained in each gap. So these are the two factors on which the final energy of the charged particle depends. Remember students, the final energy of the charged particle that is coming out of the accelerator will mainly depend on the number of gaps and it also depends on the energy gained in each gap. Okay. Now let us look into what are the limitations and advantages of this linear accelerator. Now let us see the advantages. Okay, so the advantages of the linear accelerator is, that is, so we get a very good collimated beam. That is, all the charged particles will be in a straight line. Okay, so that is the main advantage, and this was the main intention of the accelerator. So during discussion of the principles of the accelerator in the previous video, so we had mentioned this point, that is, we should get a good collimated beam. So this can be achieved, that is, since the accelerator is a linear accelerator, so we get a very good collimated beam. So second one is, there is a second advantage of this linear accelerator is, so it is economical basically. So that is, it is very economical to obtain a high energy particle. Economical to obtain high energy particle. So these are the advantages of linear accelerator. So first one is, the advantage of linear accelerator is it gives a well collimated beam. And the second advantage is it is economical, or it is quite economical to set up the linear accelerator. So with very less expense we can get a very high energy particle. So these are the advantages. Now let us look into what are the disadvantages of this linear accelerator. So the first disadvantage of this linear accelerator is, so the length of the accelerator becomes inconvenient. Why? Because if we have n number of gaps, okay, or n number of increasing length of the tubes. So if we are having more than 10 or 20 number of tubes, so then it becomes very risky or very cumbersome to handle the setup. Okay, and we have to maintain vacuum in all those large chambers. So that is the length of, that is, since we are having increasing length, so we have to maintain the vacuum in those things. So that issue will be arising to a very larger extent. And the ion current, okay, that is available in is very for a short impulse, okay, because ions are injected at an proper moment itself. So therefore the pulse of the ions, or the current pulse that you are getting, is very less. Okay, or it is very short. Okay, so first one is the length. Okay, so length becomes very inconvenient. So as the number of gaps, the number of tubes goes on increases, so what happens, it becomes risky to maintain the vacuumness of the tubes in each and every tube. And since the length is increasing, so it becomes little bit difficult to handle the equipment. So that is the first disadvantage or limitation. And second one is, since we are using ions, okay, so the ion current that is available, or the current pulse that is available, is very short impulse you get. That is at the output what you get, the energized particle. So it is having a pulse which is very less in time. Okay, so therefore why? Because we are having, or we will be injecting the charged particle in a very appropriate moment. So therefore the pulse at the output you get is very short at time. So these are the two advantages of linear accelerator. So in the next video we will be moving on to the another accelerator. So thank you.